right. Good afternoon, everyone. This is Karthikeyan Balasubramaniam from Oregon National Lab. Today, I'll be presenting about one of the use cases that we developed using Helix. Specifically, I'll be talking about the adaptive Volt-VAR control at high PV penetration and its impacts on transmission system voltages. So before I get started, I just want to let you guys know that I'll be bouncing back and forth between two domains. One is power system, and the other one is a co-simulation framework. So feel free to stop me in case I don't do a good job of explaining certain concepts. All right. So this use case is aimed at improving the understanding of interactions between transmission and distribution system through co-simulation. Specifically, we want to look at the voltage regulation function of smart inverter in regulating the transmission system PCC voltage. One of the recommendations of smart inverter working group is that a DSO should be able to adaptively change the Volt-VAR controls on the smart inverter, right? So that is one of the schemes that we want to study using this framework. We wanted to start small with a small test case. Just 1 second. Apologies for that. So we wanted to start with a small test case, get things right, and then scale up to a bigger case, right? So we started with the 9-bus test case, as you can see on the screen. It has 3 different load centers. We model each load center with one process of GridLabD. And each process of GridLabD uses a 13-node, IEEE 13-node feeder to simulate that particular load center. So we run a quasi-static time series analysis from using data from California Independent System Operator. And we do this at every 5-minute interval. So for an entire day, we're going to have about 288 dispatches. The transmission system simulator that we use for this use case is Argon's P-Flow. It is a high-performance parallel power flow solver, and we use PNNL's GridLabD as a distribution system simulator. So when we talk about co-simulation, there are 2 things a co-simulation framework is supposed to do. So one is inter-process communication. As you can see, this particular use case runs 4 different processes, 1 P-Flow instance, and then 3 GridLabD instances, right? So these processes need to talk to each other, and that is accomplished 100% through Helix. So Helix allows us to pass message from the transmission system to all of the instances of GridLabD, and vice versa. So here I'm going to talk a little bit about the interaction protocol that we used. So what we do here is we first simulate the transmission system simulator, get the voltages at the load buses, then transfer those voltage information to the feeder that is concerned. For instance, if I'm looking at bus number 5, I would transfer the voltage at bus number 5 to that particular instance of GridLabD that is simulating the feeder for that load bus. So once I do that, we do know that the loads of the distribution system are voltage sensitive. So they change as a function of voltage, right? So depending on the PCC voltage that we set, we're going to get some level of complex power injection at the PCC. So we take that information and then we transfer it back to the transmission system simulator, and we iterate this process until we get stable boundary condition, right? So the good thing here is that the results that you get using this protocol is fairly accurate when compared to the loose coupling protocol. The downside is that you have to do a lot more computation because each iteration you need to do a power flow solve on both the transmission and the distribution system simulators. One of the other things that I talked about, which is supposed to be done by a co-simulation framework, is time management, right? So time management is a tricky subject if the simulators that are part of the co-simulation, all of them have a different time step, right? So in this case, both the transmission and the distribution simulators have a same time step of 5 minutes. As I like to call it, it's in sync with each other, and that each time step, that is each dispatch, it does the tight coupling protocol. Moving on, I'm going to talk a little bit about the Volt-VAR scheme that we want to analyze here. So we wanted to specifically analyze 3 different scenarios, right? So we wanted to analyze different levels of PV penetration. So we started with 10%, and then we scaled up to 30% with respect to the peak load. Then we scaled up to 50%. And we did this at different levels of stress in the system. So we started with the base case, then we increased the loading by 50%, and then we increased the loading to 200%, and then For all of these three cases, we studied the three different penetration scenarios, 10, 30, and 50% of solar. And we studied three different control architectures. The first one is a unity power factor for the solar, for the smart inverters. The second one is a Volt-VAR curve based approach. But in this second approach, the Volt-VAR curve does not change during the course of the simulation. So we set the curve a priori before starting the simulation, and then we let it be for the entire course of the simulation. The third one is an adaptive Volt-VAR case, which is directly from one of the SIWG Smart Inverter Working Group recommendations, which is the DSO should be able to change the curve that you see on screen right here based on the conditions that is prevalent at the system at that point in time. So those are the three architectures that we studied. So this is one of the interesting results that we got from this use case, right? So on the left, what you're seeing is the three load centers versus 5, 7, and 9. Each one of them, you're seeing the voltage response for the three different control scenarios that I just described, which is the unity power factor, Volt-VAR, and adaptive Volt-VAR. And on the right, you're seeing the load curve and the solar generation curve for the three load centers. So what is interesting about this case is the unity power factor, as you can see, has voltage violations of 5 and 9, and we define a voltage violation in this case as anything that goes below. If the voltage drops below 0.95, then it means that there is a voltage violation. We want to control that and keep it within the band of 0.95 to 1.05. So when we applied the Volt-VAR control case with the fixed Volt-VAR curve, only bus number 9 had a voltage below 0.95 sometime during the simulation, right? And the third case is the adaptive Volt-VAR case. So the adaptive Volt-VAR case is exactly the same as the Volt-VAR case until the violation happens. So as you can see, here at about like 1700 hours, there is a violation at bus number 9 where the voltage drops below 0.95. As a result, the blue curve that you see is actually differentiates itself from the orange curve, which is the Volt-VAR setting, the second control strategy that we did, right? So the point to remember here is that only load center 9 had the adaptive Volt-VAR setting kick in, but you can see the response of buses 5 and 7, the other two load centers, also change as a result, right? So that means we are capturing the coupling of a control action on one of the feeders transfer to the rest of the feeders, right? And this can be explained, this has a natural explanation. So if we were to do only a transmission system simulation, right, what essentially is happening is we are reducing the amount of reactive power consumption at one of the load centers, right? So as a result, the voltage at the different nodes are going to change based on the sensitivity. So, so that is what we're seeing. But the core simulation framework allows us to do two things in particular. One is it allows us to study the voltage dependence of loads. So if I set a different voltage at the PCC, point of common coupling, then the total load injection is going to be different, right? So that is number one. The second one is it allows us to evaluate any control strategy that we have with greater detail. Because if we model everything as a spot load, then there's really not much we can do with control, right? So those are the two things. So one other quick note that I wanted to add here is the adaptive Volt-VAR case is supposed to look at the sensitivity based on the conditions prevailing at a given point in time, right? So for a given dispatch, we should be able to calculate the sensitivity. But that incurs a lot of computational costs. So instead what we did was we took a nominal case, which is the base case, and we pre-computed the sensitivities for that base case, right? Now, the directional information for this sensitivity is in the same direction, whether you calculate for a particular condition or you pre-calculate. The reason for that is we do know that the QV sensitivity, if we inject Q, the voltage has to improve, and if it's otherwise, we are at a voltage collapse situation, right? So the directional information is correct, but the actual exact sensitivity is inaccurate, or in other words, like we don't have exact information. But for this test case, that worked out fine. But moving forward, we would like to change that to computing at each given dispatch. And as I said before, we started with a small test case. We wanted to get things right, and then scale up to a bigger case. And Helix allows us to scale. The source code basically remains the same, and we almost very similar, and we can scale up to a bigger case, and that's what we want to do as a future work. So with that, I'll will you guys ask any questions that you might have at this point?
All right. Thank you, Karthik. Appreciate it.